Well, hello. Welcome back, everybody. Today, we're going to look at something very cool. The unit circle. So much power. So much potential. So much math upon its foundation. Man, I mean, how do I get into this? How do I get into the unit circle? We're going to look at two rays. So a ray, right? We got a line from a point and going off in an infinite direction, going in a direction infinitely. When we're using rays, we're keeping it simple. Okay? You don't have to use rays, right? But it's nice and simple. And we just want to relax, you know. But then there's another ray that intersects with our first one. Interesting. When we look at this, we see that there's something that kind of calls out to us. These rays, there's some sort of way they are oriented. In this scenario, we could have all kinds of setups. They look different, don't they? Different orientations in two-dimensional space. What do we make of this? How can we categorize, so to speak? How do we quantify them? Well, there's two ways that I know of. Maybe there are more ways. Maybe there are an infinite amount of ways you can decipher the orientation. But there are two prominent ways. One is a classic, right? Let's say you have this graph, okay? Fiddlesticks. If you put this on the graph, perhaps if we know their slopes, we could distinguish them based on their slopes, right? This has a slope, this has a certain slope, meaning rise over run. X over Y. It is a straight line, right? The direction doesn't change. It's constant. At any point we take its Y value and we put it over its X value and we get the rate, so to speak, that it is rising per amount it is running, so to speak. And then if we know the slopes of both of these lines, well, we can imagine, we can decipher their orientation based on that. You know, this has a slope of maybe 1, and that has a slope of 2. This has a slope of m, and this has a slope of n, you know. But something seems inefficient already, right? This is a slope of 1, 2. Seems kind of dumb. I don't know. Something's not right. I've got a much better idea. What if we choose one of the lines and we orientate it with one of the axes? Doesn't really matter which one, I suppose, but I don't know, something about the x-axis and something about its positive direction seems nice to me. Let's go with that. All right, so ray number 1 is over here. Well, ray number 2 will be over there, let's say. And now ray number 1, it's very simple. All right, we don't have to do anything. We're just gonna, it's always, we can say, you know, it doesn't really matter. It's obviously gonna have a slope of 0. It is kind of like the base. So what really we're paying attention to here is the slope of ray number 2, okay? Now we have simplified, okay? Before, we had to compare two slopes. That was kind of confusing. Now, it's more like we are looking at one slope, pretty much. And it doesn't matter. You can kind of flip it over, and then this is ray number 2 and this is ray number 1. Yeah, sure. You could even rotate it down, right? So it'd be ray number, so that would be ray number 2. So ray number 1 would be facing a different direction, right? So there's different ways you can orientate it, even while using the positive x-axis. So now we can see the slope, so to speak. And here it's very simple. Oh my gosh, the rise and the run. This has a slope of m. Okay. Very cool. Very cool. Now we're getting somewhere. See, we're building this foundation from which we know some things, and then we know more things, right? That is how math works. That's one way to distinguish the orientation of two ray segments, two rays, I should say. What's another way? Well, maybe this way was more intuitive to you guys. We see these different rays. It's like the space in between the rays can vary. But the more you go out, the larger they grow apart, the further they grow apart. Man, so it seems a little complex. It's not totally straightforward. What distance should we choose? Should we be as close to our point as possible? Should we choose some arbitrary distance? I don't know. How should we do this? Should we say it's like a line, right? And then like the distance of that line is a way to distinguish how these lines, how these rays are orientated with each other. But then how far in should we go with that? I don't know. What if, no matter what, it will always be a fraction of the circle? And we could see the further out we go, the bigger the circle gets, but it's the same, it very much appears to be the same fraction of that circle. And of course it is. If we have done math on circles, right, we know that the circumference of the circle is proportional to the radius. If the radius grows, the circumference grows. Going straight up where it's to a 90-degree angle, how do you know at what point, at what height you're going to reach your other ray or line segment or line? Yeah, tough question. Oh, man. I've got an idea, though. I don't have an idea. I stole the idea from math class, okay? What if we put a circle on a graph? We combine them into some sort of super math. Yeah, that is the idea behind the unit circle. We construct a circle on a graph to keep things simple and to keep things as versatile as possible. We give it a radius of 1, such that the entire circumference of the circle is 2 pi. All right? Why make the unit circle have a radius of 1, you ask? Well, in a way it's a bit arbitrary, but essentially it's convenient, right? If you know the relationship between like a given angle and let's say the x value, or no, let's say the y value, right? We'll choose the y value here. When the radius is 1, if you had a larger circle, let's say a radius of 10, well, then it becomes easy. Just as you would multiply this radius by 10, you would then just multiply your y value by 10 as well. And so you could easily calculate the y value of that system. It's stuff like that. That's why we have our radius of 1, basically. Okay, so how do we translate from the world of angles to the world of slopes. Slopes slash y values slash x values, right? Now that we've combined our graph and our circle into the unit circle with a radius of 1, we have to establish some ground rules. When is the angle 0? At what point on the graph is the angle 0? All right. We have chosen, probably because most people back in the day, and thus most mathematicians, were right-handed, we have chosen the positive x direction to be 0 degrees or 0 pi, or 0, right, in terms of its angle magnitude, okay? And we have also chosen to go counterclockwise as we add magnitude. So, this right here would be a 45 degree angle, or pi over 4, okay? And then this right here, a 90 degree angle, or pi over 2, that is going, as we get bigger and bigger with our angles, we're going counterclockwise around the unit circle until we come back over here, which is pi over 2, and that would be the same thing as if we had 0, okay? It's cyclical, obviously, in that nature. What we want to know is, can we transfer? If we know things about the graph, right, such as its y value or x value of this line or the slope, right, can we know the fraction of the unit circle that it takes out, right? Imagine that. You see that right there? That fraction of the unit circle. Its angle, essentially, right? Can we transfer between worlds? The ability to do so would give us so much power. Ideas, the amount of equations, oh my God, it's amazing, truly amazing. If we were to use science, science, terrible, we could create a physical model of the unit circle and take a ruler and a protractor. We take the ruler and measure these lengths. We measure the fraction of the circle, and we can transfer between there. So obviously, from our line segment here, from the center of the circle, or 0, 0, all the way to the edge, we can then, at that point that it intersects, we can either go perfectly down, all the way down to the x-axis, right, where this forms a 90 degree angle, and y 90 degrees, because we want the y value. If we go down to the x-axis, that distance that we traveled, that gives us our y. And then the opposite, if we go over to the y-axis, that distance right there, that we go over the y-axis, that gives us our x value, okay? So we could look at that and measure that, and then measure, oh my God, it turns out when x is 0.7, no, stop it. Put away your protractors, put away your rulers. In math, we never measure anything. It is all variables. Imagine if you try to calculate pi by what? You're gonna measure how long it goes around the circle? Don't be ridiculous. No. Obviously, that's a bad idea. You would never do that. No. There must be a way to calculate. If we know the angle, there must be a way to calculate the slope of the line, or its x value, or its y value, right? One of those three. All of those three. And vice versa on the unit circle, right? On the unit circle, we know that the distance between the center and the edge, of course, is 1, okay? We can use the Pythagorean Theorem there. So we have here x squared plus y squared equals 1, because we've defined that as the radius, okay? So this length is always going to be 1. So if you know the x, you then know the y, okay? You can calculate the y, and then you'll know both, and then you can calculate the slope, right? M equals y over x. You know, that's very cool. In fact, you guys may, some of you astute, very observant viewers might be looking at this and say, okay, right here, if we plugged this into a graph, we would actually get the unit circle. It's brilliant. It's truly brilliant. We're using the Pythagorean Theorem to construct a circle. We're saying, basically, when we have our x value squared with the right y value, whenever those two combined in that way equal 1, we plot it on the graph, right? So when x equals, I don't know, let's just say 1/2 maybe, okay? Y can't be anything because it has to combine, remember, in the way it has to equal 1, okay? Then let's say y, I don't know, maybe it turns out to be the square root of 3 over 2. I don't know, maybe. You know, we square the 1/2, we square root of 3 over 2, okay? We add them up, it equals 1, okay? So we do that with everything. So between, obviously we have a domain and a range. The domain is between x equals -1 and x equals 1. And the range is the same, all right? It's going to be when y equals -1 and y equals 1. So we're obviously not going to waste our time really with x values outside that range. And if you do this with everything, you can construct a circle, the unit circle, not just any circle, the unit circle on a graph. Very cool. Very cool indeed. Now, of course, this isn't a function, right? There's nothing being a function. There's no dimension being a function of another dimension in this, right? Y and x are kind of both equal in terms of which one's independent or dependent, right? We can change that, okay? What we're going to do now is we're just going to subtract x squared from both sides of the equation, and what we get is y squared equals 1 minus x squared. We can take the square root of both sides, like that, and we get y, oops, I almost wrote something on the exponent, equals the square root of 1 minus x squared, okay? Now, of course, it's actually y equals plus or minus the square root of 1 minus x squared. That would break it technically being a function, okay, because we're getting two answers, basically, except for when x equals 1 and -1. Who cares? I don't really care about that. For the sake of the video and for the sake of simplicity, we're just going to say y equals the positive square root of 1 minus x squared. What that's going to do is that is going to construct us a semicircle. So it's going to be this instead, okay? So the bottom part, the negative part, essentially has disappeared, it's gone. Okay, we're just left with the positive part, okay? Sure, and you can work with this. It's fine. It's fine. Obviously, when you have angles greater than pi, greater than 180 degrees, you're just going to have to, at this point, imagine it's dipping, let's say it's 270 degrees. Well, that's very similar to a 90-degree angle in a lot of ways, okay? We can kind of flip, the values flip over, right? So for every x value, what would the y value be? It would be whatever y value you get here, just negative. So it's easy. It's not difficult whatsoever, okay? Now, with this right here, we can have our base of operations, okay? We have an equation that gives us potentially the exact value, right? It's awesome. What if, let's say, we had the x value, right, to a certain point, and we want to know the fraction of the circle. There is a way to calculate this. And that is, again, using the Pythagorean theorem. Truly, the Pythagorean theorem is like one of the great pillars of math. Trigonometry, the unit circle, would be lost, hopeless without it. Because not only do we use the Pythagorean theorem to construct the unit circle, we also use the Pythagorean theorem at first, right? And it is our kind of first, and there's other ways, there's better ways. This gets in the realm of calculus. We can split let's say we have a curve here. We can split the curve into, we can approximate the length of the curve by splitting them into triangles. Let's say we want our delta x to be, 0.1, right? So it's always 0.1. We can calculate that now. We can put that in and we can know the y. I'm not going to go too far into this, but by doing the x squared plus y squared equals the hypotenuse here, but like we're not doing it for the unit circle. We're to construct the unit circle. We're doing it to find out this length here. We're basically splitting a curve into multiple straight lines, right? I'll make it more exaggerated so you could see. You see, we can use this to approximate. If we know the exact length of each of the straight lines and add them all up, we can approximate the length of the curve. And the obviously, the bigger you do it apart, the farther they're apart, basically, by this extension, the bigger your delta x, right? Then the more inaccurate you're going to be. You want something where it's like very close. Look at that. You can barely, it's so close, you're going to get a super accurate answer when you get to delta x, all right? And if you want to make delta x like as close to 0 as possible for the best, most accurate answer. And if you do this, you can convert, indeed, between, like in our example here, we have the x value, but you could also do it for the y value. And you can convert between knowing that and knowing the fraction of the unit circle, the angle. And then you could even turn this around. If you know the angle, let's say your angle is pi/4, okay? You can then actually do the same thing. It's kind of the simplest way to do it, is to do the same thing up until when you add up your line segments, you stop once you reach pi/4, basically. And then your total accumulated x values, you add those all up, and then you can then figure out what the x is, right? It's horizontal value, it's x value. We have now a way. In fact, this is the last thing. We have names for all of these, okay? Upon the unit circle, we have these fundamental concepts. We simplify the process I just showed you. Your calculator basically does all the math. This is when we can use things called sine, cosine, tangent, etc. Okay? We're going to say that the sine of theta being our fraction of the unit circle, the angle, is going to equal the y value over the hypotenuse, which in this case equals 1, which basically means the y value. So this is an operation where you give the calculator, right? You are given the theta, the angle, and you get on the unit circle. Remember, we're focusing on the unit circle here. All right, I know you guys are screaming, no, sine is opposite over hypotenuse. SOHCAHTOA is dumb, okay? Because SOHCAHTOA is all hyped up and encumbered with, it's all triangles. They think triangles are the be-all, end-all. Obviously, triangles are important. We use triangles. We use right triangles, the Pythagorean Theorem, and all that. Heavily integrated into this, I know, but I want to stay in the realm of the unit circle, right? So the opposite, no, it's the y. The cosine of theta, our angle, will give you x over 1, which just equals x. Okay, now we have tangent theta. That is the same thing as the sine of theta over the cosine of theta. Now, sine of theta we've established as y, so that's just going to be y, and then cosine of theta we established that's x, y over x. Tangent theta equals y over x, which equals the slope, n. The rise over run, okay? So the tangent of an angle will get you its slope. This is the thing we wanted. We wanted this. We have a couple more things to go, and then we're done, okay? We have things like arc sine, okay? The arc sine of the y value on the unit circle, okay, on the unit circle, is going to give us the angle. So if we know the y value at a certain point, we can use arc sine to calculate the fraction of the unit circle that corresponds to that y value. Now, of course, this does get confusing, okay, because there's going to be two of them, okay? So, you know, let's say our y is square root of 3 over 2. There's actually two different points where y equals positive square root of 3 over 2. So basically, you're going to have to know the context of such a thing. Yeah, so the arc sine is going to give you two different answers. And in reality, the arc cosine, when you take the arc cosine of x, that will also give you theta. This also it has two different values, right? So it can either be, when it comes to the x, there are two positive x values. Let's say, you know, it's, I don't know, square root of 2 over 2. All right, there's two different angles, and they're vastly different. One is a 45-degree angle, and then the other is 315 degrees, okay? Or whatever. Yeah, okay? So with that, you will basically need context, okay? Don't worry too much about it. In reality, sometimes math, like the square root of 16, it's two answers. There's positive 4 and negative 4, okay? Sometimes math gives you two possibilities, all right? Last but not least, the arctangent of the y over x will also give you theta, meaning the slope. The arctangent of the slope will give you the portion of the circle, the angle, portion of the unit circle, okay? With these fundamental, there's more to it, you know, there's more to it in trigonometry. You know, what if you have the inverse of sine? We call that secant, right? And so you can get fancy with it, but these 6 operations are the fundamental operations of trigonometry, and they relate to the unit circle. Okay, that has been my video on the unit circle. I hope you guys have enjoyed, and please, please, please remember, this is power. This is like magic, but in real life, okay? I hope you guys truly understand and respect the awesomeness that is the jewel of math, the unit circle. I know I got hyped up a little bit in this video. I said it'd be a calm video. That was a lie. I am sorry. I get way too excited sometimes. All right. Peace out, everyone. Bye.